Hi, I'm Kim, and this work is done with Jung-Mi Park and Uichin. Recent advances in AI agent enable a variety of proactive or system-initiated voice services, even in driving context. As recently, vehicle manufacturers have started considering proactive AI agent with more intelligent, advanced, and human-like proactive behavior. In vehicle services, need to be convenience as well as that. Current AI agents don't consider interruption timing when delivering voice services. However, in driving context, delivering voice services at inappropriate moment can cause cognitive distraction, leading to distract driving, which is deadly. Unfortunately, many accidents have taken place due to the distract driving. There need to be a context-aware in-vehicle system or AI agent that deliver voice interaction at the opportune moment, in which the negative effect of voice interaction can be minimized. To build such a system, we first need to understand opportune moment for proactive voice interaction in driving context. In this study, we aim to broaden our understanding of opportune moment for proactive voice interaction in driving context by examining first how proactive voice task demands under diverse driving situation impact driver interruptibility. Second, how the driver adaptive behavior during the interaction are related to driver interruptibility. To address the research question, we used interruptibility dataset collected from our previous study. The data were collected from 29 drivers while they were engaging in proactive auditory-verbal or voice secondary tasks with various interruption contexts, such as three varying levels of secondary task demand and diverse driving context. For interruptibility measure, we consider composite model of interruptibility. The composite model allowed to measure driver interruptibility from various perspectives. It consists of three interruptibility dimensions, namely overall perceived difficulty, auditory-verbal performance, and driving safety. We first analyze how the second task demand and the maneuver type affect three interruptibility dimensions in the composite model of interruptibility. These three graphs present percentage of interruptible moment for each interruptibility dimension across second task demands and for representative maneuver type. The previous study on interruptibility having considered the effect of second task demand. Our results highlight that in addition to the maneuver type or driving demand, second task demand also significantly affect driver interruptibility. Furthermore, the change trend in percentage of interruptible moment differ considerably across interrupted dimension, especially between driving safety and other interruptibility dimensions. For example, as the second task demand increased, the percentage of interruptible moment for overall perceived difficulty significantly decreased. This was also true for auditory-verbal performance. However, for the driving safety, when the maneuver type was straight or turn, the percentage did not significantly vary or show any difference across the second task demand. This difference could be attributed to the adaptive behavior. Next, we further examine what kind of adaptive behavior the drivers show and how the adaptive behavior are related to interruptibility. We found that drivers employ several adaptive behaviors to manage their interruptibility and to ensure driving safety. The two common adaptive behaviors were speed reduction and reducing engagement in second task. We further statistically examine how those common adaptive behaviors impact driver interruptibility. Drivers commonly report that they reduce their speed when engaged in second task. The graph shows that the speed reduction pattern across maneuver type and interruptibility. Drivers reduce their speed to a great extent for turn than for straight and lane change, while the speed reduction was greater for interruptible than uninterrupted cases. These results indicate that regardless of maneuver types, the speed reduction behavior improves driver interruptibility. Drivers commonly report that they cease to engage in second task whenever they need to pay more attention to driving. This behavior was common reason for low interruptibility cases in which drivers have answered incorrectly. These three heat maps present percentage of drivers who correctly answer each item in the second task across different maneuver type and second task demand. The map shows that percentage decrease as the item order increase and decrease further as the second task demands increase. In addition, when the second task demands are high, the percentage of the latter item is lower when maneuver type change in the order of stop, straight, turn, and lane change. These results indicate that when the second task demand is high, Drivers are more likely interruptible in terms of auditory-verbal performance as the duration of the task decreases. Based on our finding, in this study, we proposed the concept of flow control for driver-vehicle interaction that can improve driver interruptibility. In data communication, flow control is the technical concept of ensuring a sender is not overwhelming a receiver by sending packets faster than the receiver can consume. Our results show that drivers are more likely interruptible as interaction demand decrease. In addition, when interaction demand is high, drivers are more likely to be interruptible for short duration of interaction. This implies that drive can be more interruptible by controlling the demand of speech interaction. In other words, flow control can be used to manage driver-vehicle interaction flow such that AI agent does not overwhelm a driver. More detail about the flow control can be found in our paper. This is the end of my presentation. Thank you.